This is our lesson number 48 in Sapphire Kingdom Gemology YouTube channel. In this video, we are learning very useful information regarding tools and lighting conditions. When we are checking the stones with lighting conditions, we use 7 conditions through the microscope. So these conditions very useful, and the tools also. So take the time and write a note and take screenshots and printed materials you have to produce. Then learn well. In this video, in this screen, here it is a garnet gemstone checking through the spectroscope. When we looking through the spectroscope, the color spectrum absorption here, see the black lines are absorption spectra. We can see when the light comes to the garnet gemstone, all the 7 colors are coming here, all the nanometers are coming here, all the 7 colors are coming here, and reflects after absorption, reflects only the red color. Then we can check the absorption lines and get the idea regarding the stone. It is garnet. If it is a ruby, the same 7 colors are coming to the ruby and reflects through the ruby. After the absorption, we are checking the absorption spectrum through the spectroscope. Then the black lines we can observe. So it gives very useful information regarding the gemstone. We can identify the gemstone. This is the basic thing. One more thing is there. It is polar, cross-polar. Before I explain this, I need to tell you the light. Light goes from one place to another place with the speed of 300,000 kilometers per second. 300,000 kilometers per second. It goes from one place to another place with vibrations, vertical and horizontal vibrations. The light rays travel through the vertical. Vertical is this, horizontal is this. Vertical and the horizontal vibrations move the light ray. Light ray is a power. It moves from one place to another place. So polarized plate, polarizer or polarized plate can stop vertical and horizontal both. If we use vertical polarizer, we can stop the vertical vibrations and send only the, after the polarizer card, we can send only the horizontal vibrations. If we use horizontal polarizer, it cuts the horizontal vibrations. So if we use both here, this is unpolarized light. The vertical polarizer is here. It uses here. Then it cuts vertical light, vertical vibrations. Then again, horizontal polarizer used here. Then it cuts the horizontal vibrations. Then after both, when we use both, no more light is there. Light stops from these two. So no more light goes there. So this is the theory we are using under the double card or polarizer. So we are using this technique to explain. Learn well. We are moving to the next slide. Before that, I need to tell you, please subscribe and give a comment and share to our youth to share these information through the generations. So we are moving to next. It is 10x triplet loop. 10x triplet loop is very useful because this is very useful tool in the gemology. when we are observing the gemstone through the 10x loop, inside this 10x triplet means there are 3 lenses are here to give the color correction. When the color comes through the gemstone, perfect color gives to our naked eye. So 10x triplet must be the loop you have to choose. If it is not triplet, you can't see the real color. So this is the standard loop for gem testing. Then another tool is diachroscope. Diachroscope, it is very thin one, maybe 3-4 inches long. When we see from one side to the other side, we can see the squares, 2 squares here. So the other side we have to put near the eye, and we can see these 2 boxes, the other side. Then we can check the stone. When we are rotating this diachroscope or the stone, the 2 colors are moving. One color is moving to one square, and the next color goes to the other square. So if we can see 2 colors or 2 shades of colors, we can see that stone is double refractive. DR stone, not single refractive. If we check this with the spinel, the same color goes to both rooms. If it is garnet, same color goes to 2 rooms. If it is a ruby, there are 2 colors moving one here, the other color goes there. So it gives double refractive. If it is a tarphite, it gives 2 colors here, then we can recognize it as double refractive, not tarphite, double refractive. So if we check this with the double card, we can see this also inside the double card. The same thing happening. Triplet, the word triplet or prismatic. The triplet loop is the industry standard. It has a whopping 3 lenses attached together for the very sharpest view. This is the only type that corrects color to making it crucial for identifying the gem correctly. Remember this. Write down all things. Then we are moving here. Have you ever tilted a stone and seen a different color than before? When we check stones, that's because of a trait called pleochroism. We learned earlier in the lesson 1, and more lessons we discussed pleochroism. In single it is vacuum. Pleochroism. When a gem shows different colors at different angles, that is called pleochroism. A diachroscope is the tool to determine whether the stone is pleochroic and narrow down the gemstone testing process further. We can use diachroscope to check the pleochroism and pleochroism color source. The diachroscope works by showing 2 colored blocks at the end of its tube. Here, if the blocks have the same color, your gemstone is single refractive gem. If it is, in other words, not pleochroic, if the blocks are different colors, you have a doubly refractive pleochroic gemstone. Very simple tool. It is diachroscope. Now you know 10x loop, diachroscope. Then the next one is here. It is, what is this? Look at those. The methylene iodide inside this bottle, it is methylene iodide. Methylene iodide has 1.81 refractive index. So we use methylene iodide liquid to place in this here, this place, and we use a gemstone with faceted gemstone or if it is a rough stone, we have to polish one facet and place it here. After that, we have to cover this. This is the cover. Then we can see through this lens. Here, this is the place. We can see. The light goes through this. The backside, we can set the torch here. Torch light we can use from here. Then we can see inside like this. There are two shadowy and light separation by the refractive index line. The scale is there. We can see this line into two decimal values or 3 decimal values. So this is called RI. For general purposes, always calibrate the reflectometer first with distilled or deionized water to 0. It is when it is by, but you don't need it. Methylene iodide CH2I2 used in a bottle RI of that is 1.81. So up to 1.81 RI, we can check all the gemstones through this stone. Then it is called, the name is refractometer. It is refractometer. We check RI. This is the stone placed here. And the light placed here. This is the place. We can put the light from here. Then we can see inside like this. When we see through this lens, we can see the light like this. So once you have done a visual analysis with the loop, you will want to measure its refractive index with the refractometer. But what is a refractive index exactly? A stone's refractive index gauges the way light bends after entering it. When light enters into the stone, it bends. It bends. So we are checking that bending amount from this refractometer. So every gemstone's refractive index or RI is constant. For instance, both sapphires and rubies have RI between 1.76 and 1.77 because they are both corundum. So refractive index is giving unique identity for the gemstone. So this is very simple and useful. So we learn 10x triplet loop and the diachroscope, and here reflectometer. Now here, what is this? You learn when you are in O levels, you learn this in school. When the sunlight comes through the prism, goes through the prism, it bends. And after that, because the sunlight coming from air, environment is air. This prism is glass prism. Environment is glass. When it enters from the air to glass, it bends, little bit bends. Then after that, from there to air again, it bends. When we use a white color single paper here, we can get the spectrum colors included in sunlight. Red, orange, yellow, green, blue, indigo, violet. These are the 7 colors inside the spectrum. I think you know it. It is here, the 7 colors. So the frequency is 400 to 700 is the visible range of our eye. It is called visible light. 400 nanometers up to 700 nanometers is the visible area. Below 400 is this UV, X-ray, gamma, and over 700 is IR, infrared, microwave, radio wave, TV wave, like that. So this side and this side we can't see. It is harmful for the naked eye. So this is called spectrum. Spectrum colors, the order is this. You have to remember this. This also same thing. When the white light comes to the gemstone and enter inside the gemstone, it absorbs something, some colors it absorbs and return red color here. So after absorption, we can see the black and red there. So when we show, we can see the stone giving red color because it reflects red color, absorbs the other colors. So after gemstone absorbs certain colors out of the 7 colors of light, the remaining colors radiate away from the stone. When those rays of light reach our eyes, we see the stone in that color. Because the spectrum gives these black or gray Fraunhofer lines to identify the light energy absorbed by the stone. The values at those places can be identified in nanometers. These are the Fraunhofer lines. Then it is very easy to identify the stone because the absorption values are constant values that vary according to the type of a stone. So it is unique value. Then I need to explain some words. Dispersion. Dispersion is this. This is diffraction. Refraction. This is refraction. This light want to go there, but the prism refract with this angle. After that, it is refract again in this angle. So dispersion, diffraction, and the refraction, we need to understand very well because we are handling gemstones with light waves in this business. So we need to understand this. We are moving to next. Fraunhofer lines. This is called Fraunhofer lines. What is that means? Gem testing laboratories make use of variety of instruments, both high, broad, and low. Of primary importance are the microscope, reflectometer, ultraviolet light, specific gravity equipment, and the spectroscope. The spectroscope is one of the most powerful instruments in the gemologist tools. The human eye contains 2 different components called cones and rods. Cones and rods. The cones are concentrated in the center of the eye and are responsible for detecting color, red, green, and blue. Cones. Rods have a greater density on the side of the eye and are responsible for detecting differences in tone, black, white, and gray. Remember, rods can identify the black color, white color, and gray color, and the differences in there. Cones can identify the other colors, RGB colors. You can find another biological lesson later. With the direct vision spectroscope is very useful thing. We are mainly concerned with tone. As a result, you will be better able to detect faint absorption lines. Faint absorption lines you can detect if you look at them from the side of your eye. When you are watching, you have to use not cones, rods. So black, white, and gray, you have to identify, you have to check with that using your peripheral vision where they are more rods rather than looking straight at them. When you are watching these Fraunhofer lines for the absorption spectra of the stone, you remember, don't watch at directly there. Use your corner of the eye. So you have to use your rods, not the cones, rods. Then rods can identify the black, white, and gray color differences. Then you can see. If not, you can't see this. So remember that. Then here it is the absorption bands, that means spectra, absorption spectra or absorption bands of some gemstones taken by using spectroscope. Fraunhofer lines in the solar spectrum. It is given earlier. These are the circle lines. Almandine garnet, alexandrite lines, absorption spectra, ruby, yellow sapphire. Some stones are mentioned here. You can identify this. And here, this is the Fraunhofer lines. Fraunhofer lines in the solar spectrum. These are used as reference points. These are used as reference points. All refractive indexes, that means N, are calibrated for light of 589 nanometers, matching the Fraunhofer D line, ND. It is physics thing. Dispersion is gemology. In gemology is measured as the difference in Ri between the Fraunhofer B and G lines. Between the B and G lines, the differences are called that. It is physics something. This is the spectrometer. This is the stone. This is fiber optic light rod. Light gives here. Then it absorbs color and gives the color in this way. You can see using your eye from here, you can see the Fraunhofer lines, absorption spectra of the stone. Eye here, this is the spectroscope, light and the stone. So this is the way. Same thing. Light comes through this fiber optic wire, and this is the same way. But we can use with the finger. We can use this small instrument to check the absorption spectra. It is not a big thing. See, this is the stone. White light consists of 7 rays, goes through the stone and absorbs some colors and reflects the color. Then when it is reflecting, absorption spectra is given black or gray lines called Fraunhofer lines. This is ruby. This is garnet. Garnet and ruby's absorption spectra is completely different. It is unique. Scanning spectroscope, once produced by GEM instruments, rotating the calibrated drum on the right of the instrument while weaving the spectrum through the eyepiece, rolls the spectrum past the crosshair. When the absorption line is lined up with the crosshair, the exact wavelength can be read of a digital LED display on the top of the instrument. This is this instrument. The instrument is excellent for measuring the exact wavelengths of fine absorption and emission lines. Now we are moving to little bit more beyond the direct vision spectroscope. Earlier we used the spectroscope. Beyond the direct vision, we use spectroscope for direct vision. Beyond the direct vision, we can use this. It is called VIS-NIR spectroscope. A spectroscope method utilizing the visible and near infrared region of the spectromagnetic spectrum. 380 to 2500 nanometers. This scale we can't see all. This is the scale we can see. 400 to 700. But increase in this level, we can see with this machine, with this apparatus. We can see it. See, this is the graph from the laptop screen. So that is called beyond the direct vision spectroscope. While the direct vision spectroscope is a wonderful tool that most anyone can afford, it does have significant limitations because we can see only 400 to 700 only. This is the only range we can see that direct vision spectroscope. Beyond that spectroscope, we can see more range with this machine. The human eye has a difficult time recognizing broad areas of absorption and also at quantifying absorption. and it is limited to 400 to 700 nanometers visible range. This is where the ultraviolet visible near infrared. So look at UV, VIS, NIR means UV means ultraviolet, visible, V means visible, VIS means visible, N for near, IR for infrared. So you can remember this UV, VIS, NIR. So ultraviolet, visible, V is the capital, the others are simple. All are capital here. Near, infrared. Spectrophotometer. It is the name of the machine. Such instruments measure the absorption and emission of light across a broad range, anywhere from 200 to 1000 nanometers. So we can see only 400 to 700 nanometers. Beyond that, 200 up to 1000 nanometers, we can get the range from this machine. So it is very useful. Now you know what is this name, UV, VIS, NIR. When you see the testing certificates, you can see this short name they have tested. Okay, we are moving to next. Look at here. Ultraviolet visible near infrared. Spectrum of a Madagascar sapphire. Before and after heating. This is before heating. This is after heating. Look at the differences there. With the absorption spectra. Wavelengths into the x-axis. See, up to 1000. Absorption confidence is y-axis. See. Then, before and after heating, areas of absorption are represented by peaks. Absorption are in peaks. See, it is 500, between 500 and 625, there is a peak. It is before heat treatment. After heat treatment, that peak is missing here. 875 and 1000, we can't see with our naked eye. So we can't use the manual spectrometer. We need this machine, this machinery to check it if it is heated or not. See, if it is goes more than 700, it is heated. The peak is moving there. So UV, VIS, NIR, this spectrometer gives us the difference between the normal, natural and the heated stones. Can you understand A and B, the difference? Sapphire, see UV, VIS, NIR spectrum of a Madagascar sapphire before and after heating. Areas of absorption are represented by peaks. Look at the peak here. Between 500 and 625 nanometer, it is a peak. Before heating. After heating, that peak is missing now. It goes there. Peak is there. It is in invisible range. We can't see. So we need this machine only. So UV, VIS, NIR can detect the heating treatment and difference between the natural and heating stones. We need this technology. So after heating, this machine can find out it. A, this is A. The UV, VIS, NIR, that means ultraviolet visible near infrared. Spectrum of sample before heat treatment is here. Note that the most prominent feature is the absorption between 500 and 600 nanometers. It is the peak. As well as a small iron-related peak around 450 nanometers. 450 nanometers, another small peak here. It is iron-related, ferrous-related peak here. Then go to B. The UV ultraviolet visible near infrared spectrum of sample after heat into 900 Celsius. After heating only to 900, note the development of a large peak at 880. This is the large peak. That 450 iron-related peak also there. See, it is also there. No change. See here. We can't see this peak with the manual spectroscope. We have to go to UVVISNI. Any lab can have this machine. They can detect the heat treatment. Remember that. Now I need to explain you again the light, how the light travels from one place to another place. Light is another energy, travels with the speed of 300,000 kilometers per second. When it is moving one place to another place, it vibrates vertically and horizontally. Vertical or horizontal vibrating rays can filter with the polarizer. Polarizer card can filter. There are two kinds of polarizer cards. One is vertical. Vertical polarizer breaks all the vertical vibrations and sends through the card only the horizontal light. So this light, red color light, not consist of vertical rays, vertically polarized light. So the vertical blue color one is filtered. Then if we use here another card, horizontal polarizer card here, then this light also filtered. It will stop. In the second picture shows us this vertical polarizer breaks the vertical blue color vibrations in the light, and the horizontal polarizer stops the other light. Then no more light goes there. This is the thing we are using to check the double refractive and single refractive stones. We use two cards as filters. So vertical polarizer is used, and there is a card called spinel card. The name is completely wrong. The correct name is double card. Double card use polarizer, one polarizer, and we have to place the stone in between these polarizer cards, and we have to rotate it. I will explain it in polarizer machine. This is called cross polar. If you forget to subscribe, please subscribe. Now look at the polarizer. Polarizer machine is this. But we don't need polarizer, because if we can use the double card properly, no need of that. To use the double card, you have to understand this. Polaroid filter cuts the single vibration. If it is the Polaroid filter is vertical Polaroid filter, it is cutting vertical vibrations in the light. Then through this Polaroid filter, it goes only the polarized light. So we use this technology to check the double and single refractive gemstones. For example, spinel is single refractive, taphite is double refractive, but lot of people cannot understand what is the difference there. I need this diagram to explain. The polariscope is this. This is the apparatus, but we don't need this. We can use the thing that double card. When we place, this is the one filter, Polaroid filter. This is another filter. In between these two filters, we have to place the stone here. The light source comes through the here, there. Light goes through this filter and enter to the stone here and goes through again, and it comes to our eye. We have to rotate this stone, or we have to rotate the eyepiece. That is the theory. The polariscope reaction of double refractive gemstones. Now look at this. There are 1, 2, 3, 4 numbers here. This is the stone in between polarizer or double card. From the other side, light comes. From the other side, light goes through the card and enter to the stone, and stone sends the light through this card and it comes to our eye. When we rotate the stone, see, this is the stone. See, this is the stone. First, it is dark. No light goes through the stone. When we turn 90 degrees, now you can see the light goes through the stone. It is light. This is black. This is white now. Number 3, when we rotate again 90 degrees, it gives black. No color comes through the stone. When we rotate again another 90 degrees, that means one cycle is finished now. Then it gives again light. So when we rotate the stone single round, one round, 4 times it will change black, white, black, white. So this is the thing. Black means no color comes here, there. So remember this, black and white, no color with color. This is the rotation. What is it? This is polariscope. The same thing happening here, polariscope. It is expensive, but we can manage this with the double card. What is it? The polariscope is a gemological instrument that tests for a gemstone being double or single with single reflective, and will allow us to find the various crystal axes of the stone. There are 3 crystal axes, X, Y, and Z or Z. You know, pleochroism is in the Z axis, Z axis, which is where is got its name for this machine, polar scope. So a scope to see the poles or axis of the stone. A scope to see the poles or axis of the stone. So it is called polariscope. Now, if you remember the section on the diachroscope, the use of plain polarized light allows us to see the different colors of light being transmitted by a gemstone. The polariscope, however, allows us to actually see the path that those beams are taken through the stone. By knowing that the stone is double refractive, we can use the optic interference figure to actually find the various optical directions that the light is traveling through the stone, and thereby make identification based on this information. Come here again. Double refractive gemstones will go through 2 light and 2 dark positions as they are rotated through the 360 degrees circle between the Polaroid plates of the polariscope, or between the Polaroid plates of the double card. In between the double card, when we rotate in the stone, one circle, that means 360 degrees. Quarter circle gives light. Dark, light. Next quarter, dark. Next quarter, light. Then it is one cycle. So, if it is not more showing like that, then turn the stone's axis. You know there are 3 axes are there. X-axis, Y-axis, and Z-axis. Check through X-axis or Y-axis or Z-axis. Then you can see one axis gives this. Which axis? It is Z-axis. Pleochroism gives through the Z-axis, that means C-axis. You have to check the stone with C-axis. Then this is the theory. You better write down it in your notebook and remember, study it. Now we are moving to dark field and bright field illumination. It is a lighting condition. Look at the lights, bright field. Lights are there. Because of this light, what happened there? Field of view. We can see this field with the light here. We can see this field with the light. When we watch from here or anywhere in this area, it is giving bright field view. We can go there, here, or here. But this light is not moving there. That side is darker than this side also. So we can see this field as dark field. If we watch the stone from here, we can see the inclusions in dark field mode. When we see the stone from here, we can see the dark field view. When we watch the stone from here or here, in this area, we can see the bright field view. Now you can understand the difference between bright field view and dark field view. It is 1 out of 7 lighting conditions I explained here. We have to watch in this dark field or light field, bright field illuminations to see the inclusions. So remember that. Now, what is this here? Look at the difference here. Dark field and light field. Look at that. See, bright field. When we watch from this side, the stone is here. When we watch from this side, through the lens or microscope, we can see the inclusions. It is bright field illumination. If we watch from this side or this side, the light goes here. And dark field, we are watching from here. Completely different vision there. So positions of bright field and dark field lights based upon. This is the bright field light. This is the dark field light. So you have to understand this very well. It is simple. Now look at this. Direct and diffuse light illumination. We know very well, but you have no idea. In your home may be there. Inside your home, maybe inside on the ceiling, you have the diffuse lights. If the light is here, this is direct illumination. If we use a single light into our room, direct illumination gives the different amount of lights to places, not the same light. If we watch from the base, this area is bright light, very bright. This is weaker. So we need evenly get the light into the room. So we need to change the diffuse material with the light with diffuse material. It is called ceiling lights. It gives the same color to whole area. That is indirect illumination. Indirect illumination gives the equal amount of light to all of the area of the room. Direct illumination gives like this. So today in houses, we are using indirect illumination with the pan lights in the ceiling. So remember, diffuse light illumination is this. This is direct illumination. This is diffuse light illumination. So we have learned 2 things now out of 7. Then what is this? Micro Raman spectroscopy. Without this micro name, Raman spectroscopy is inside Sri Lanka we have. But micro Raman we don't have any place in the Sri Lanka. We don't have this. This is the apparatus. It is very expensive. So Raman spectroscopy is different than the micro Raman. So micro Raman is more expensive test. And if we need to test with micro Raman, we have no facilities inside Sri Lanka. So remember that. So this is the technology we are using. If you are interested, you can find this. And this is the machine. Raman spectroscopy, named after Indian physicist C.V. Raman, is a spectroscopic technique typically used to determine vibrational modes of molecules. Inside the gemstone, there are molecules, we know. Inside the molecules, there are vibrations. So we can check the vibrational modes, although rotational and other low frequency modes of systems may also be observed through the Raman spectroscopy. Raman spectroscopy is commonly used in chemistry to provide a structural fingerprint by which molecules can be identified. Raman spectroscopy can be identified through the gemstones molecules. So it is very useful thing. Here we are learning some emission and detection. Look at the word emission. The light comes, then some light will transmit inside the material. Some will absorb inside the material. Some are fluorescence. This light goes like transmission, absorption, and fluorescence, and diffuse, and reflection. When it reflects, we can detect it. This is called detection. Diffraction, polarization. So you have to understand these words: emission, detection, transmission, absorption. This light is transmit through the material to the other side. Absorption, some will absorb by the material. Some will fluorescence. Some will diffuse. Some will, after the inside the diffuse, we can reflect it. We can detect it. Emission, detection. So you have to understand the words. Now look at this. Properties of light. This is completely, all the colors are reflected. So this is called reflection. All the colors are absorbed by the material. So it is called absorption. This is all the colors are moving through the material to the other side. So that is transmission. You need to understand these three properties well. And more properties here. This is the gem microscope. We can connect to the laptop and see this picture from here. So two eyepieces are there. This is the stone holder. We need this light is giving only the transmitted light. But when we buy the microscope, we need to understand fiber optic light must be there. It is very useful. Okay. Now, oblique illumination. Oblique. You know the meaning of oblique illumination. A and B. See, A and B are different. Same stones inclusions. Watching different way. What is oblique illumination? Oblique illumination method when direct illumination is restricted to 1/2 of the visible field and relief is somewhat low. Bright fringers here. Dark fringers. Bright fringers and dark fringers from the edges of mineral fragments in an immersion oil beneath a cover glass. It is inside the immersion oil. A and B, the difference we are discussing here. If bright fringers from one edges of the mineral fragment A facing toward the darkened side of the visible field and dark fringes facing the bright side of the field, the refractive index of the mineral fragment is greater than that of the immersion oil, the refractive index of which is known. Which is known, refractive index is there inside the oil. So if we see this oblique illumination, so immersion oil, the refractive index of which is known is the oils one. If bright fingers from one edges of the mineral fragments facing towards the darkened side of the visible field and dark fringes facing the bright side of the field, the refractive index of the mineral, this mineral fragment is greater than the oils one. If it is B, see the B, if dark fringes, these fringes, from one on the edges of the mineral fragments facing towards the darkened side of the visible field and the bright fringes facing the bright side of the field, the refractive index of the mineral fragment is less than that of the mineral oil. It is less than. This is greater than. Oils are refractive index is known. It is greater than. This is less than. So oblique illumination. It is oblique illumination. Oblique in singular word, it is anatha, allow, oblique illumination. Now, I represent the lighting conditions needed for the upcoming lessons as a summary. Diffuse light field, that means transmitted light, 1. 2, dark field plus diffuse fiber optic. You know the dark field and light field earlier. Next, light field plus oblique fiber optic, oblique. 4th one, dark field plus crossed polar. You know the crossed polar. Next one, 5th one, fiber optic plus diffuse oblique. 6th one, dark field plus overhead fiber optic. Last one, shadowing. We are watching the shadow. These are the 7 lighting arrangements. We need to watch the inclusions from next lessons. So you have to remember and write down in your note. This is the microscope. This is very, very advanced microscope and very expensive, $25,000. So if you forgot to subscribe yet, please subscribe and share this to send this knowledge to our youth. Now, in the next lessons, we will learn how to identify inclusions in natural and heated sapphires and other gemstones when tested using lighting conditions. We have just learned 7 lighting conditions. Then we will meet in lesson 49 inclusions video. So please subscribe. Don't forget to subscribe. We will meet on next lesson.